everybody, welcome to the 8th video of the particle system series. So this is the third video in which we use the transmorph feedback system with shaders, and in this video we're going to see a couple of things. First, we will see how we can prevent the particles from just disappearing from our window, so we will limit the position of the particles in a certain area. And then we are going to see how to assign a mass to the particles using random numbers and textures connected to the GGLTF object. And if we still have time, we're going to see how we can use some other random numbers to set an initial velocity or a random velocity at every frame for the particles. Great, so let's start. This is the current status of the system. The particles will just go right and down according to our two forces that we created in the shaders, which are gravity and wind. So first thing we are going to do is to stop the particles from just disappearing outside the window. So we have to basically wrap the position of those particles inside a certain area, as we did with JIT-Gen when we were still working with JIT-Gen. So we will do it in this way. We will create an if statement. So we can say if O position, and then we switch the epsilon component of the particle's position, so basically where the particles are on the vertical axis. So if this is less than minus 1.0, so let's say that our world is a cube of 1 unit of size, then, and we can do it either with brackets or without brackets, if it's a single line. For the moment we will do this with curly brackets, and we will go a bit deeper into how if statement work in another video, so for the moment don't mind too much about it. So if the epsilon position of the particles is less than minus 1, if we want to wrap them, for example, we can say that O position dot epsilon is multiplied equal to minus 1.0. So what does this mean? It means that if the particles are of a position that is less than 1, we multiply the position dot epsilon by minus 1, which will change the sign of the number, so the particles will appear now at the top. So let's save and let's see if this works. Exactly, so as you can see, this is working because the particles are appearing here at the top once they go below minus 1. Now the only problem we got still is that the particles are still going to the right, so we have, and disappearing on the right, so we have to fix these as well. So let's create another if statement. So if O position dot x is greater than 1.0, or, and we create an or statement, which means either if this condition is true or the next condition is true, then do what's inside the curly brackets. So we will say or O position dot x is less than minus 0.1, so they are too much on the left. Then let's open the curly brackets and let's do the same thing. Let's say O position dot x per equal minus 1. Sorry, forgot a comma. Will give us an error. Exactly. Great. So as you can see now, when they go on the right, they will basically reappear here back on the left. That's how we can wrap the position of our particles. We could also create a variable. Let's create a variable which is a float, which is the cube size. So let's call it this cube world size, and let's assign to 1.0, and then we will use these instead of using a fixed number. So instead of having every time to change all these numbers, we will just change the value inside this cube world size. Mind that I'm not changing this minus 1 because this is just to reverse the sign of the position, so it doesn't matter which number it is, we just need to reverse the size or where the position is in order for it to reappear on the other side. Just to be very thorough with it, let's do it also on the epsilon. Let's also say or O position dot epsilon is greater than cube world size. Then it will reverse it, and let's do it also with the zeta value. So we got it for all the three axes. So e position dot z is greater than cube world point size or is less of minus cube world size, then O position dot z, it's getting reversed. Okay, great. Now our particles are confined in a cube of size 1. We can also make this cube bigger by setting the sizes to be 2, but for the moment let's keep it to 1. One thing we could do is to encapsulate all this thing inside the function, so we don't have to have it all the time inside our main function. So let's create a function, and you can check how functions work in this other video about functions in GLSL that I made. So let's do it like this. This function will return nothing. This function will return nothing because we are going to modify the variables directly as a reference. So let's call it like check edges. We are going to get inside the vector 3, which is our position, and also the cube size, which is a float. So cube size. And let's actually call it cube world size, so we don't have to rename it. Great. Then let's take these lines here, and let's put it inside the function. Great. Now instead of position, we need to call it position, because position is our placeholder for whatever variable comes inside. So we need to use the name of the placeholder inside the function, and we need to use it as a in-out. So this means that we are going to either read this variable, but also we are going to write to this variable. So the in-out keyword means that we are using this variable both to read from it and to write to it. So with the in statement, it means we are reading from this variable, and the out statement, it means we are also writing to this variable, which will retain its value also outside of the function. So it's like passing by reference inside C or C++. The same case in GLSL. So by default, every variable that is marked as input, so for example the cube world size, even if we don't specify that this is an input variable, it's by default marked as input. We can also specify it explicitly. And great, this means that we are not going to write to cube world size because we don't need to modify this variable. We just need to modify actually the position. Great. So let's call this function here, check edges, with our position and our cube world size. Let's see if this works. Okay, great. So it's working, as you can see. The function is writing inside the position variable, and we are retaining its values also outside of the function. Great. Instead of having the function body up here, one thing that we could do is to actually copy it, put it at the end after the main function, so at the end of our shader, and then we simply can declare it up here in the shader, but actually not describing what it does, and then we can describe what it does at the end of the shader. So this is a common feature of C and C++ and a lot of other programming languages, that we can actually declare the function in a certain place, use it, but then state what the function does after we actually used it. So if we don't put this line here, if we comment this line, for example, it will give us an error because we are using the function before actually declaring it. But if we simply declare it, but don't write the body of the function, we can already use it, and then we can declare it afterward. So this is allowed, and this is nice for us because then we get all the space at the beginning of the shader free. So this is the declaration of the function, and that's the definition of the function. Okay, great. Now let's implement a mass for the particles. So we are going to connect a texture to the transform feedback shader. So in order to do this, we need to declare a new parameter here at the beginning of our shader description. Let's actually change the name here into TF particles shader, and let's change also the description into, let's keep it empty for the moment. Okay, great. So we'll create a new parameter here, param name. This will be random texture, so text, random text, which means is a texture that is just full of random numbers. This is going to be of type integer because texture inside the GLSL in max are of type integer, which is basically the index of this texture. And then we give it a default value of 0. So this is not a parameter that we get from the max application, so we cannot call it with a state keyword. We need to define it ourselves and then define also a default value. So we will give it a default value of 0. This is not a parameter that we get from the application, so we cannot use the state keyword. We can just use the default to give it a default value. In this case, it's the index 0 because this is the only texture connected to the shader for the moment. So we give it the number 0. Good. Then we need to bind it. So bind param random text, okay, to program VP, because that's our vertex program, the only one we are using basically. Great. Then we need to declare it in our shader as a uniform of type sampler 1D. So because we just got 1000 particles in a single dimension matrix, we can actually assign a one-dimensional texture to this shader, so we can read this texture using the index of our vertices, so of our particles. We'll see this in 1 second. So we then write the name of our uniform texture, which is random text, we said. Great. Now we actually need to create our texture inside the patch. So let's get down here and create simply a JIT noise for planes float32 1000, so 1000 one-dimensional matrix with 1000 cells into it. Let's also connect it to a load bank. And then let's create our texture, so JIT GL texture, which throws to TF particles, the name of our context, is of dimension 1000, and type, we can say the type, we can set it to float32, this doesn't really matter. And then we need to give it also a name. So name, let's call it random text. It doesn't need to be the same name as in the shader, but it can be the same name. So we just need an identifier that identifies this name of this texture inside the patch. Great. Then let's go inside the transform feedback object and let's say texture. We can give it the texture attribute and assign random text as the texture assigned to this object. Great, my Max just crashed because I tried to execute the TF shader and somehow something went wrong with it just after attaching the texture. So if it's the case for you as well, don't worry, because it's kind of okay. It actually works. Great, so let's go inside our shader now and let's use the values from this random texture as our mass. So let's sample this texture. So let's create a float variable, let's call it mass. Then let's use the texture function. Now the texture function in GLSL 3.3 will sample these textures using some coordinates. So this texture is called random text. So the first argument to this function is the name of our texture. The second argument is an index in this texture that we want to sample. So in order to sample this texture, we can use the built-in variable inside GLSL, which is called GL vertex ID. So this is the index of every one of the vertices of our particle system. So the particles are basically vertices in our mesh, and every vertex, every particle has its own index. So we are going to use this index, which is an integer number, so 0, 1, 2, 3, 4, and so on, to sample this texture. The only thing is that sampler 1D textures come inside the GLSL with normalized coordinates. So it doesn't matter if you don't assign rectangle 0 here in the texture, is anyway you need to use normalized coordinates to read it. So let's actually divide this by 1000, because then we get coordinates between 0 and 1, because the index will go between 0 and the number of particles minus 1, so we actually should divide this by 999 in order to go between 0 and 1. And then we switch only the first random number, because we need just one number to define the mass. Great, so let's save. Great, seems that it's working. Now our force formula was mass multiplied by the acceleration, so which means that if you want to get the value of our acceleration, we need to say that the acceleration is equal to the force divided by the mass. Now, the random numbers by default generated by JIT noise are between 0 and 1. So if we will divide the force by a number between 0 and 1, the force will actually get bigger. So let's first multiply the mass by a value, for example, of 10. And then we can say mass plus equal to 1. So let's actually multiply by a value of 9, so the random numbers now can go between a minimum of 0 and a maximum of 9, and then we sum 1 to that, so now the numbers can go to a minimum of 1, maximum of 10, because we sum an offset of 1. So we do this because then we are sure that we are never going to be dividing by 0, because dividing by 0 in computers always yields some strange results. Great. So let's actually now fulfill our formula and say that the acceleration is equal by the force divided by the mass. So let's divide gravity by mass and wind by mass. Now, as you can see, our particles are going much slower because the initial force that they had has been divided by a number between 1 and 10. But as you can see also, they are all moving at a different speed. In order to make this a bit more clear, let's make the gravity force much bigger. So as you can see now, some particles are moving faster and some are moving slower because all of them now have their own mass. So some will have a bigger mass and fall faster, some will have a smaller mass and fall slower. Let's make also our wind force a bit greater. Great. So let's for one moment remove the wind from the acceleration. So we just have our gravity force acting on our particles. Now, as you probably already realized, there's something wrong in this function that we created, because we say that the acceleration is equal to the force divided by the mass. But we know that actually in the real world, it doesn't matter which is the mass of an object, they will all fall at the same rate. And that's because the gravity force works with the mass of the object. So in order to have this formula really correct for gravity, we should actually say that gravity is multiplied by mass and then divided by mass. That's how it actually works in the real world. So this is why our formula was not correct in the real world. But if we just don't care so much about this and we just want to say, okay, objects actually that have a bigger mass fall actually slower than our with a small mass, that's correct for other forces, like for example the wind, because the wind in this case correctly will move, let's remove the gravity for 1 second, the wind will now correctly move particles that are smaller faster, and particles that are with more mass will move slower, which actually is the same as in real world. So the gravity force is a special force that takes also into account the mass of the object. We will see how to implement the gravitational attraction better in the next video. So great, let's reinstate our fake gravity thing. Great, so we didn't have time to actually use the random numbers as a force for the particles. We will do this in the next video. So in this video we saw how we can wrap the particle position inside a cube with a certain size. Then we saw how we can connect a texture to a shader, to a transform feedback shader, how we can declare the texture as a uniform. I actually like to call my uniforms with a U in top of the name. So, sorry, I didn't do it before, let's do it now. So U random text, exactly, because then we know that this is actually a uniform, which means is a value that we declare ourselves from outside the shader, so from our max patch. Great. And we sample the values of this uniform texture, which is a sampler 1D, so it means it's a texture with one-dimensional texture. We sample this texture using the texture function here, which takes as an argument the name of the texture and then an index in normalized coordinates between 0 and 1 to read the texture. And then we switched only the one component of this texture, which could be the x, the y, and so on. The texture has 4 planes, is a vector 4, so every pixel of this texture has 4 values, like a matrix with 4 planes, and we use this as the mass for which to divide our forces in order to fulfill Newton's second law. Great! So this was the content of the video. I hope you found it useful. As always, if you liked the video, you can subscribe to the channel, check out my Instagram account, Facebook account, and also my Patreon account, where you can join the community, have access to the patches that I create in my tutorials 1 week before everybody else, and also access to a big amount of other patches, which you can actually also find on my website, federicofoderaro.com. Here you can find all my video tutorials, pretty much ordered, also with tags to search for them, and you can find also my patches as well with the tags, so they're pretty easy to look through. So thank you very much for following, and see you soon in the next video, where we're going on with the transform feedback shader and we're going to implement some cool stuff. See you soon. Ciao.